Now that we've covered the main operations based on our array implementation of add and get max, now we're going to look at some ways that we can sort. And the first one we're going to look at is a priority queue sort. So remember, we're using heaps to implement priority queues. With our fast get max, we can also sort any list quickly. So we're going to put all the elements into a priority queue. We're going to call get max n times, and that gives us all the elements in descending order. Possible for any priority queue implementation, but it's only really worth it if it's going to be fast. Okay, so let's have a look at it. So the idea, if we're using a heap, remember that the add was n log n multiplied by each of the comparisons. If we look at the get max for a heap, it's n log n multiplied by the comparisons, so it's the same. So therefore, the total for a heap implementation would be n log n plus n log n, which equals n log n. And if we say putting them back into the list is on as well, then it's pretty much the same complexity as quicksort and merge sort. Well, particularly I guess with the case of quicksort on its best case. So advantages of priority queue sort is it works well with any implementation of priority queues. It requires n space for the new queue. Disadvantages is the heap construction, which is done in n log n time. So let's look at a different approach on perhaps doing a bottom-up construction. So the idea, cleverer, is a bottom-up heap construction. We've been constructing the heaps one element at a time. After each element is added, we heapify the entire heap to make sure that it's in the correct sorted order, and that's n log n per element added. If we happen to know many elements in advance, we can do it more quickly. Recall that a binary search tree is recursive. A binary search tree is an element plus two children that are also binary search trees. Remember, heaps are also recursive. A heap is an element with two children that are both heaps. Every circle is a heap. And obviously there's more in this diagram, but the idea is obviously each of these nodes and this subtree and this one here, they're all heaps themselves. They both maintain the principle that they're complete and in the correct order. So to build a heap, we can start from the bottom and make little heaps. By definition, every node is a heap, so leaves are already done, less work. In a complete binary tree with n elements, how many leaves are there? So if we think about this, we don't know if the bottom level is complete, as in all the elements are filled there, but we know that the number of leaf nodes will still be the combination of the last level and n minus 1. So it's roughly n divided by 2, but in the case where we only have one out of two nodes, we may have to round down. So if we do integer division, it's essentially half would be leaf nodes. So let's have a look at an example here. So basically, like I was saying, we know that we've got at least these ones and the ones on the previous level. So we've got 5 leaf nodes in this example, and you can see there's 5 non-leaf nodes. The first non-leaf node is the parent of the last element, right? So there's that one, which is E in this example. So let's do the bottom-up construction. Start with an array in an arbitrary order. So here's an example here. And build subheaps starting at the bottom right. The leaves are already done, so we just start at 12. So this one here. Now that we've identified 12 as the first one we're going to look at, we need to pick the biggest child and then work out whether we need to sync it or not. So in this case, 12 will need to be synced down and swapped here. So now it's finished. Now this is a heap. Similar with this one. So we go to the next element at index 5, compare with its parent. Sorry, we get the parent, which is this one here, 9, and then we decide whether we need to sync down by comparing 9 and 17. In this case we do, so it swaps there. Now we do the next one. So again, we're going to get the next parent, which is 1 here. We decide if we get the biggest child, which is 17. We decide if we have to swap down or we need to sync. Yes, we do. And then again, 1's going to then compare with the biggest child, which is 9, and we can see that 1 is less than 9, so we will need to sync down. Now we've done it for the subheaps, the overall tree is now a heap as well. It is both complete and in the correct order. So let's look at an alternative init for known elements. So if elements are known in advance, they're in the array, assume that max length equals the length of the array if given. So again, we're going to do it based on this array. I mean, we probably don't need to compare against the min capacity, but anyway, for the sake of it, we're going to have to make it one bigger than the array because obviously we skip index 0. The length is equal to the max size, which if not given, we can assume that it will be equal to the length of the array. So if an array is not none, as in it's provided, then we're going to copy all the elements one by one, and we're just going to remove it up one position. And now that we've added them, they're not in the correct heap order, so what we're going to have to do is heapify every parent. So the idea is we start from the end. Remember, divide by 2 to get the first parent, and then we just walk backwards through our array, not including 0, right? We're going to stop at the root node, but the point is we would then sync the nodes, the parents, into their correct position in the heap, just to make sure that they're in their correct position. So if we look at the complexity here, it's going to get a bit complex, but hold on tight. Imagine that these represent each of the levels in the tree, and where this is the number of nodes, and this is the height, or the maximum height that it needs to sink down. So if we look at the bottom level, which is at the height minus 1, we know it doesn't need to sink down at all, so the height would be 0. But if we were at the second last level, well, then it would need to sink down 1. So that's we know that's the height. If we're at the second last level, well, then we know that it needs to go down 2, a maximum of 2 sync operations, and etc. And if we knew that we're at the root node itself, well, then obviously it needs to sync based on down on the height minus 1. So that just gives us the idea at each level on the maximum number of sync operations that we'd need to do. So if we were to sum them all up, now remember we don't care about the bottom level because again we don't need to sync them. But if we start at the second bottom level, and which are the parents per se, and that's this level 2 to the h minus 2, we know that the height is 1, and then we just need to multiply it by the number of nodes that are on that level. So that's, in the worst case, that would tell us at that level if all the nodes on that level had to sync down based on their height, we'd multiply them together. Again, we'd go to the next one and we'd do the same. So for each of these levels, we multiply the number of nodes by how many times we'd need to sync them in the worst case. So that would give us this formula here. And if we were to simplify that, let's take that equation again, and we're going to multiply it by 2. So this we've just multiplied this expression by 2. And what we're going to do is now we're going to realign them so that they line up nicely. So we've got 2s and an s here again. So it's the same equations, just realigned so that they're nicely aligned there. So it'll be easier for us to apply simultaneous equations to do the subtraction here. So what we're going to do is if this was equation 1 and this was equation 2, we're going to do 2s minus s, and then that should give us this equation here. Obviously this one would just stay the same. 2 minus 1 is 1, then we get the same in the brackets. Obviously if the h's would cancel out, minus 3 minus minus 4 is positive 1, minus 2 minus 3 would become positive 1, and so forth. And obviously this one would be the last one that would be here, but obviously when we minus it, it would become a negative. We'd negate it. Then if we expand the brackets, we should get something along these lines. So then all we need to do is expand these brackets as well, and that would give us this. And then if we combine them all together, really the majority of this would just become to the h minus 1 and then minus h. If we consider the number of nodes in the tree, it's 2 to the power h, where h is the height of the tree, minus 1. So that means, if we work that out, then if we replace that, then that's n minus h. So therefore, the complexity, or the upper bound, can be provided as on, where n is the number of nodes in the tree. So that just proves that this approach therefore is ON. So that obviously is better than doing it as n log n. Hopefully that made sense. Feel free to step through it a bit slower if it didn't, but that's the end of this video. In the final video, we're going to look at an in-place heap sort. We'll see you then.